Hello, everyone. This is the uh, second talk in the Higher Structure Seminar Series. Today, our speaker is Professor Mas Mas Masanori Morishita, and he obtained his PhD from Johns Hopkins University in '92. His thesis advisor was Takashi Ono, and his dissertation topic was toward non-abelian Kummer theory. He is currently working at Kyushu University, and he is one of the founders of arithmetic topology, which has gained importance recently. Let's welcome him for today's talk.
Okay, thank you very much. Thank you very much for the invitation, and I'd like to thank the professors Ikeda for their kind invitation. I'm very happy to join this seminar and to meet everyone in the Zoom online. So I'm going to talk about arithmetic topology and arithmetic TQFT. TQFT means topological quantum field theory. Okay, so the contents of my talk will consist of two parts. Can you hear me? Okay.
Yes.
The contents of my talk will consist of two parts. The first one is arithmetic topology. And I explain the basic ideas as motivation and some historical backgrounds. And then as an application, I choose the two topics as features related to the class field theory in number theory. The one is a higher order linking numbers of primes. The other one is a topological class field theory for three manifolds. Then I go to the second part is arithmetic TQFT. And I review first the topological quantum field theory and the diagram fitness theory. And then I present our results on arithmetic diagram fitness TQFT, and which is based on the arithmetic Chan-Simon theory, which was started to be studied by Myung-Hyun Kim. Okay, so let me start the arithmetic topology, the first part. Arithmetic topology. Okay, and so what is arithmetic topology? Yes, it is a new research area in mathematics which investigates the interactions between the number theory and the three-dimensional topology. Okay, as which is based on the analogies between three manifolds and number link and the knots and the primes. So let me explain that just briefly, the historical background on this subject. I think this may go back to the work of Gauss in the 19th century. He studied the quadratic residues, arithmetic of quadratic residues in the beginning of the 19th century in his youth. And later, he studied the linking number in electromagnetic theory. But, however, after Gauss, the number theory and knot theory or mathematical physics have been developed separately for a long time. In fact, the quadratic residue have been developed to the class field theory in number theory, and the linking number in electromagnetic theory as maybe regarded as an abelian Chan-Simon's TQFT now. Then after Gauss, it takes almost 1.5 centuries, and in the middle of 19th century, the topology and number theory was bridged by the work of the Tate, Nakayama, and Grothendieck, and Archin, Verdier, and Maser, the result may be phrased as a topological interpretation of class field theory. Okay, so let me recall their result in the following as a following dictionary. So first, the circle and the finite field. So as you know that the finite covering of the circle as a category of finite covering of a circle is equivalent to the category of finite étale algebra of a finite field. To be more precise, the circle is homotopy equivalent to the Eilenberg-Maclaurin space with KZ1 or the classifying space of BZ. And similarly, the prime spectrum of the finite field has the same étale homotopy type of KZ hat1 Eilenberg-Maclaurin scheme, and or the classifying scheme of Z hat, where the Z hat is a profinite completion of the additive group of the ring of integers, rational integers. The second, the solid torus and boundary torus or boundary torus and periodic integers and periodic numbers. Solid torus, let me denote it by V in the following. V represents a solid torus. Is S1 cross the two-dimensional disk. S corresponds to the periodic integers at the spec of the OP. This means a ring of periodic integers. And V is homotopy equivalent to the circle in the core of the solid torus, the same as the periodic integer has a core circle is a finite field, spec of the finite field. And the boundary torus is given by the space removing the core circle from the solid torus. You say you can crush the solid torus, the circle, the core circle, and the torus, the boundary torus. This is boundary torus. Similarly, if you remove the spec of a finite field from the spec of periodic integers, then you get the spec of the periodic field. So these are correspondence or analogous objects. And for solid torus, we have a two-dimensional Poincare dualities. The same, we have the two-dimensional, similarly, we have two-dimensional Tate duality for the periodic fields. And actually the torus fundamental group of the boundary torus has a presentation which is generated by meridian loop and the longitude loop, and they are commute. The relation is just a commuting relation. Similarly, we have the Tame local Galois group of the periodic fields. This is a maximal Tame quotient of the absolute Galois group of the periodic fields. And it is generated by the two elements, the monodromy and the Frobenius, and which subject to the relation of the monodromy to the power of norm p minus 1, and this is the commutator of tau sigma equal 1. This is a theorem by Iwasawa, the classical theorem by Iwasawa. Okay, so now, thirdly, we have analogies between the three manifolds number ring. Actually, three manifolds satisfy the closed three manifolds satisfies Poincare three-dimensional Poincare duality. Similarly, for number ring, the spec of OK, the ring of integer of number field K, satisfies the three-dimensional Archimberdier dualities. So these are similar. So these analogies, 1, 2, 3, leads us to the analogies between knots in the three manifolds and the primes in the number rings. Okay, this leads to the arithmetic topology, that bridge between three-dimensional topology and arithmetic. The subject was initiated to be studied systematically by Mazer and Misha Kaplanov and Alexander Resnikov, and independently by myself in the 1990s. And the results are the basic analogies, as sometimes called M square KR dictionaries. So let me give you this dictionary.
Excuse me, just in the previous slide.
Okay.
The fundamental group of the torus group, when you M and L, isn't the fundamental group of torus normally free group on two generators, and then the generators don't necessarily commute, but the first homology group is abelianization of the fundamental group. Then
the fundamental group itself is abelian because torus. The fundamental group of torus is Z cross Z. It's generated by meridian and longitude. Because torus is S1 cross S1.
Okay.
One S1 circle is meridian. It's called meridian. The other one is longitude.
Okay.
Okay. So okay. Meridian is a null homologous in solid torus, but longitude is not. But longitude is null homologous outside the torus, okay? Outside torus. That is a distinction of meridian and longitude, okay? I'll explain it later on.
Okay.
Okay. Is it okay for you? Maybe this is basic thing, so maybe I should be more to be more precise, but is it okay?
I mean, if it's not the most important thing in your talk, we can come back to it later. I mean,
okay.
Okay. I mean,
okay. Now it's okay. Now let me give you some. The M square KR dictionary is between the three-dimensional topology and the number theory. So in this side is topology. It's oriented closed, connected closed three manifold M as a correspond to the compactified number ring. It's let me denote it X of K. X of K denotes the union of the spectrum, prime spectrum, the ring of integer of number field, added by the infinite primes. Okay, we compactify the spec OK by infinite primes. And these infinite primes as correspond to the end of non-compact three manifold. Okay, as a notion, there is a notion of end in the three manifold, and the end correspond to the infinite primes. The knots and the primes, as I mentioned, and the tube neighborhood of knot correspond to the periodic integer ring. The boundary torus as correspond to the periodic fields. And peripheral group means just a fundamental group of boundary torus. Is correspond to the local absolute Galois group. And the link correspond to the finite set of maximal ideals of number ring. And tube neighborhood link correspond to the union of periodic number integer ring. The boundary tori of the tube neighborhood of link correspond to the union of finite set of periodic fields. Okay, and the link complement as correspond to the complement of finite set of primes. Okay, the link group is link group is just the fundamental group of link complement. It correspond to the ether fundamental group of the complement of finite set of primes, but it is a maximal Galois group with given ramification on S. Okay, and the boundary map from two chain of M to the two chain from M to the one cycle of M by taking the boundary of the two chain correspond to the making the principal ideal. So from A to the principal ideal generated by A. So the first homology group is just this co-kernel. So the correspond to the ideal group is the co-kernel of the making the map of making principal ideals. And the second homology group is just a kernel of this map. So the kernel of this map is a unit group of number ring. So we have these the basic analogies from between the three-dimensional topology of number theory. Okay, based on these basic analogies, we can develop some analogous theories in both sides. So now this arithmetic topology is a driving force to obtain the analogous results between the three-dimensional topology and number theory. Okay, let me explain why I started to study this analogy. What is my own motivation to study this analogy? Yes, that is coming from the analogies of number fields, function fields. It has been known since 19th century, there is analogies between number fields and function fields. Okay, I learned this when I was a student. And here, prime of number fields correspond to the point on a curve of a field or a point on the Riemann surfaces classically. But we notice the followings. The complex valued point of and then this spec OK is called the arithmetic curve in arithmetic algebraic geometry. Okay, and then the complex point of this arithmetic curve is just a homomorphism on the ring of integer to C. This is a finite set because only finitely many infinite primes. While the complex point of the curve C is a Riemann surface. Certainly this is an infinite set. This is a continuous infinite set. So there is a difference between them. And moreover, there is no analogy found between the étale fundamental group of spec arithmetic curve. Pi1 of spec OK is same as a maximal unramified Galois group, of number field K. And Pi1C is this fundamental group of the curve C. There is no analogy. Actually, when F is finite field, the base field of curve is finite field, then we have an exact sequence. This is a homotopy exact sequence. And so this exact sequence shows that C looks like a surface bundle over a circle because the fundamental group of circle is Z hat here. But however, the fundamental group of spec OK is much more random. That this doesn't have such a structure. It's sometimes finite. For example, spec of the quadratic field Q square root 5 or some Q square root -5 or something. These are all finite and it's very random. And it is similar to three-manifold fundamental group, closer to the structure of three-manifold fundamental group. Moreover, let me notice one more thing. The fundamental group of the complement of prime number in spec Z determines the prime. Okay, if the fundamental group of spec Z removed by the P and the fundamental group of Z removed by another Q primes is same, then P must be equal to Q. We can show this by class fields using class field theory. Why? The fundamental group of the complement of affine line is analogous object of spec Z in arithmetic geometry. But if you remove affine line to the point on the affine line, doesn't depend on the choice of P and Q. For any PQ, the fundamental group is the same. But here it's a number theory side, it's different. If Q and Q are different, then these fundamental groups are different, very different. So prime numbers has a very strong personality, prime numbers. While it's the P points on the curve is, how do you say, doesn't have a personality. It's the same, any point is the same. So spec OK is closer to three-manifold group from this point of view, and the primes looks like a knot. And then the complement of the spec of the ring of integer of finite set of prime is closer to the hyperbolic C manifold for large S, suggested by Noki Ikeda-Uchida's theorem on the absolute Galois group of K. Absolute Galois group is obtained by projective limit, inverse limit of the fundamental group of spec OK minus S removed by S, and the rigidity of hyperbolic C manifolds. So from this point of view, spec OK is more like a three manifold and the primes look like a knot. That was a motivation of my work. Anyway, based on these basic analogies I mentioned, like this by this dictionary, I will discuss the higher order linking numbers of primes as an arithmetic applications. Okay, first let's recall the linking number of knots. Let K, the union L, be the two-component oriented link like this picture. This is one knot. L is linked to K. And in this picture, the linking number is 2. Linking number is how many times L is linked around K. In this picture, this is just 2. Okay. In terms of algebraic topology, the linking number is interpreted as follows. Let xk be the complement of one knot K. Okay. This is a complement of one knot K from S3. The note that K is null homologous in S3 because S3 is simply connected. Then this implies that the homology group, not the complement, is generated by the meridian loop. Okay, this is a K. So not the complement is like this. Then the homology group, not complement, generated by this loop MK. Okay, this loop MK. This is the generator of the complement. And there is a Seifert surface of sigma K, which whose boundary is not K. Okay, this is a picture. Then the linking number is given by this formula. The L is linking number times of the meridian in the homology group. Okay, so let me see that this is a linking number is 2 because L is linked 2 times. This means L is 2 times this meridian leap, 2 times. Okay. The another interpretation is just given by the intersection number of L and sigma K. So this intersection number is 2. Okay. So this is another interpretation of linking number. But it depends on the orientation of K and L. But mod 2 linking number is only 0 that takes value as a 0 or 1 is independent of the orientation of K and L. Let us define the mod 2 linking numbers primes based on our analogies. Okay, let P be a prime number that considers a prime complement of prime numbers in spec Z bar. Then, in general, this P is not mod 2 null homologous, but P is null homologous in spec Z bar. This bar means a spec Z union of infinite primes. And that means that the complement of the homology, étale homology of XP with coefficient F2 is just F2. This is equivalent to the P is congruent 1 mod 4. Because if P is congruent 3 mod 4, then we cannot have the unramified covering, étale covering of XP. If P is, for example, if P is 3, then Q square root 3 ramified over 2, not only 3, 2 and 3 ramified, but only one prime P is ramified if P is congruent 1 mod 4, and the homology group is given by the Galois group Q square root P and over Q. And this meridian loop corresponds to the monodromy, which sends the square root P is minus square root P. this tau p is like this monodromy loop for p. If p regards a knot, this tau p is monodromy. Okay. So suppose, so now let's PQ be the distinct prime numbers congruent 1 mod 4. Then we define the linking number, mod 2 linking number of P and Q as a monodromy of the Frobenius over Q in the Galois group. The Frobenius is a loop around the Q. So Frobenius, if Frobenius over Q is tau p times some mod 2 number by this relation, then we define the linking number in this way. This is a way that defines the linking number of prime numbers, just in the same way as in topology. So we have two possibilities. Linking number is P and Q is 0. The linking number is 1 in these cases. Okay, but look at this. Okay, this is 0. Linking number is 0 or 1. Okay, if linking number is 0, if and only if the Frobenius is 0 in this Galois group, that means identity. So that means that sigma p is acts on the sigma q Frobenius sends the square root of p to the minus square root of minus p. That means p is quadratic residues mod q. So hence we have the mod 2 linking number is nothing but the Legendre symbol. Legendre symbol. Okay, so this is our example. These 29, 17, 5, and 13, and 149 linked in this way, maybe called Olympic primes, Olympic prime numbers, like this. Okay, and we have also the intersection number interpretation of the Legendre symbol. So consider the monodromy representation of the fundamental group of this complement of prime number P in spec Z to the Galois group over Q square root over Q. This may be seen as a homology class of H1 of the XP to étale homology class with coefficient F2. But arch-inverted duality, we have this rho P defines a Ziphius surface H2 homology of XP. And by the duality, as arch-inverted duality again, the Frobenius loop, which lives in this side, defines the element of H2 compact supported H2 homology. Then we have to take a cup product that is mod 2 intersection number. Then this is the same as, we can show this is the same as mod 2 linking number we defined before. Okay, so in this picture, the sigma q is linked in that this is a Ziphius surface, or sigma p. I'm sorry, this should be sigma is print. This is sigma p. It's sigma q is linked in the sigma p once, if and only if sigma p linked with sigma q as this picture shows. So this means the linking number of P and Q is the same as linking number of Q and P. But this is nothing but quadratic reciprocity law of P and Q and Q and P. So this is a topological interpretation of Gauss reciprocity law. Okay, this picture shows the Gauss reciprocity law. Okay. So from this point of view of arithmetic topology, class field theory is nothing but homology theory to describe the how primes of a number of fields are linked. Okay, so recall that homology theory is abelian theory, the theory of abelian coverings. So next we go to the non-abelian theory, the non-abelian, particularly the nilpotent homotopy theory. Okay, so first look at this link. It's called the Borromean link. This link is all linking number. Any of these two knots are 0. You see, maybe you can see that any of these two nodes are unlinked, but we cannot separate these three nodes. So this is non-trivial link, but any of two are trivial link, doesn't link. Okay. So in order to prove that the Brownian link is not trivial link means components of separated, can be separated. Milner introduced the higher order linking numbers, the called Milner invariants. Mu is written, denoted by mu I1 to IN for any link L in the three sphere, which satisfies the following properties. Mu of ij is just a linking number of k and kj. So the mu I is defined if the all Milner invariant mu j is vanished if the length of these indices is less than the length of I. Okay, so in this sense, the Milner invariant is higher order linking numbers because mu ij is a usual Gauss linking numbers. And we can show that the Brownian link, the linking number, any of these two are 0, but the triple linking numbers, Milner invariant mu 1, 2, 3 is not 0. So that means that shows that this is not trivial link. This is a way the Milner showed that this is a non-trivial. Okay, so ingredient, a key ingredient to define the Milner invariant is the following theorem by Milner on the structure of the link group. So let L be the R component link in S3, and the XL is the complement of the link. Then this nil means a nilpotent completion. Nilpotent completion of the fundamental group of the link complement is generated by the meridian around Ki and subject to the relations M1, L2, MR, LL. This means this is just a relation of the boundary torus of the each node. Okay. From using this presentation, Milner introduced Milner invariants. Okay. Actually, the meaning of Milner invariant is given as follows. Okay. The linking number is abelian invariant because the linking number is defined by using homology group, just only homology group. But Milner invariant is a nilpotent invariance in the following sense. So for commutative ring R, we set HNR denotes the group of unipotent upper triangular matrices. Okay, this is an important group. Then the theorem by Murasugi says that let L be a link, R component link on S. Suppose the Milner invariance of nu I is there if the length of I, this indices, is less than n. Then there is HNZ, here is a Z. So this is an important covering of over S3, which is ramified over link K1 to Kn minus 1, such that nu of 1 to nu of this is length n is defined and it is monodromy along Kn. But it can be shown this is in the center of this group. Center of this group is just only this entries are here. So this is Z. So this is in a sense the meaning of Milner invariant in the covering theory. Okay, so now let's move to the arithmetic side. We define the mod 2 Milner invariant of primes. So let S be the set of R distinct prime numbers. All of these are congruent to 1 mod 4. And let XS is a complement of this S in spec Z. And consider the Protz et al. Fundamental group of this complement of prime. This means the maximal Protz-Galois group of rationals unramified outside S and infinities. Okay. Then by Koch theorem by Koch says, this is arithmetic analog of the Milner's theorem on link group. This Protz-Galois group has a presentation like this. Okay, this is generated by monodromy over P1 subject to these relation. These relation is coming from the tame local Gala group, coming from the tame local Gala group over pi adic fields. Okay, this is the tame Gala group. So from using this representation, just as in the topologies, topological Milnor invariant, we can define mod 2 Milnor invariants of nu2 of these things. So then my theorem that suppose all Milnor invariant is less than n, then there is a Hn Z mod 2n. This Hn is the same one. This is here we take a Z mod 2, F2 in this ring. Extension of a rational, Rn over a rational number fields, ramified over primes P1 to Pn minus 1, such that nu2, mod 2 Milnor invariant, is just along the monotomy along Pn, which is in center. So this means nu2 of 1 to the n equals 0, if and only if Pn is completely decomposed in Rn. This is completely decomposed Rn. So example is R equal n equal 2, then R2 is just quadratic. This extension is Z mod 2 if n equal 2. And then the Milnor invariant is not nu2 1 2 is nothing but the Legendre symbol. Okay. And suppose R equal n equals 3, and suppose nu2 ij is equal 0, then R3 is this extension adjoined by square root of P1, square root of P2, and the square root of x plus y P1, where xy is a integer solution x square plus P1 y square equal P2 z square. And it can be shown that this is a unique dihedral extension of a rational of degree 8, unramified outside P1 and P2. This is shown by my student Amano. And minus 1 to the power of a new triple Milnor invariant, mod 2 triple Milnor invariant, coincide with the triple symbol introduced by the Ledai in 1939. He's a Hungarian, I think Hungarian mathematician. But this is very classical invariant in algebraic number theory, but this gives a topological interpretation of his triple symbol. So, okay, for example, 5, 97, 90, 29, and 181, 13, 61, 937 is links like this. It's Borromean primes. Any of these two are Milnor invariant 0. Legendre symbol is 1, but Milnor invariant is just 1. These things, 1. Milnor triple invariant 1. Okay, here is a case of R equal n equal 4. This result due to my student Amano, former student Amano. Suppose nu over I equals 0. Then nilpotent extension R4 over rational is a degree 64 and unramified outside P1, P2, and P3, and can be constructed concretely. And nu2 of 1, 2, 3, 5, 4 describes the decomposition law of P4 in R3. Okay, and the definition of R3 is very complicated to describe here, but here is an example. If P1, P2, P3, P4 is 5, 101, 8081, and 449, then this R4 as a degree 64 extension of a rational is given by this extension. And then any of the linking number of 2 primes, any of triple linking numbers of these, any 3 has triple linking number 0, but the fourth tuple Milnor invariant is non-zero, 1. So these primes 5, 101, 881, 449 links like this. This is called Milnor link. This very famous link in link theory. Okay. So let me give This leads us to define the multiple quadratic residue symbol. The P1, P2 to Pn can be defined by the -1 to the power of our mod 2 Milnor invariant. Okay. Then here is a problem, so maybe for thesis. Can you construct the Rn concretely for any n? Okay. N equal 2, then very classical Gauss's result. N equals 3, we have Redai's triple symbol. N equal 4, we have Amano's result. But in general, we don't know how to construct Rn in general. This gives the arithmetic meaning of the multiple quadratic residue symbols. Okay. Can we extend the theory over any number field containing nth root of unity so that nth power residue symbols are generalized to multiple way? Okay. We don't know what this theory. The only result, only known result is the case of number field is Eisenstein number field, q square root minus 3. Q square root minus 3. This is the result myself and Mizusawa and Amano. And the third question is most important. For permutation S of 1, 2 to the n, are there any relations amongst these multiple quadratic symbol for the by permuting S1 to permuting 1 to n? Because this would be a generalization of, if you find such a relation, this would be a non-commutative reciprocity law, generalized Gauss quadratic reciprocity law. Gauss reciprocity law is P1, P2 equals P2, P1. So this, we can change this, the Gauss reciprocity law. So if you prove such a relation, symmetries of these symbols, that would be non-commutative reciprocity law, generalizing Gauss quadratic reciprocity law. That's most important. But here I notice that, okay, this Rn is just a nilpotent extension of the rational number field. Just only nilpotent extension. We deal with only nilpotent extension. So for such a finite nilpotent extension, I'm not familiar with the things, but I think Lagrange's program is also verified, already verified by Arthur Crozell. But their results of non-abelian reciprocity in their sense, the Lagrange program doesn't give such a reciprocity law. This is a different direction. It's a different thing. Maybe more, it's rooted in more classical algebraic number theory. This is okay. Certainly, it is important to study the relation with Lagrange, the things, automorphic forms of this non-commutative reciprocity law. But I'm not familiar with automorphic forms, so I don't know anything. So the next issue on the arithmetic topology is topological class field theory for three manifolds. So let me start with to pose a fundamental question in arithmetic topology. Is namely, what set of nodes in S3 is topological analog of the set of all prime number 2, 3, 5, 7, and so on. Okay, this is very fundamental and the basic question, but it's difficult. But if you take the all nodes in S3, if you take all nodes in S3, then it is uncountable set. It's continuous set because not is yeah. So it is not an analogous object of the set of all prime numbers. So what set of prime nodes is a good set, maybe good, very, very, very good set of nodes in S3, which correspond to the set of all prime numbers, because the set of all prime numbers has a marvelous, nice structures, such as a product formula the Hilbert reciprocity law, and so on. So we want to find such a set of good knots, the good set of knots in S3, which satisfies similar results, similar properties. And also, can we develop the idyllic theory for three manifolds? Well, this is a basic fundamental question in arithmetic topology. And this question was, in some sense, answered as my students, the Nibo Ueki and Mihara. He's not my student, but they gave her an answer and they established the idyllic class field theory for three manifold in these two papers. Whereas Nibo and Ueki introduced a notion of very admissible link. This is a link of infinitely many countable components. Also, Mihara introduced the notion of stably generic link. It has also the infinitely many countable component. And strictly stable generic link is the refined notion by the admissible link. And these, so stably admissible link is plays a similar role to the set of all prime numbers, all primes in the number field. So the definition of stably generic link is maybe a complicated. A link of L of countably many components in the three manifold M is called a stably generic link if for any finite branched cover of M over a finite sublink of L, for any finite sublink L of H inverse L is a component of H inverse L minus, this is bold L, sorry, my misprint, this is bold L. This is bold L. This is a standard L. This is standard L. Oh, sorry. Maybe this is bold L. This should be bold L. This should be bold L, like this L, like this L. So I'm sorry, I made a misprint. Anyhow, maybe it's not so important to remember this definition, but you can just think of the stably generic link is an analogous object of the set of all primes in three manifold. And Mihara said the stable generic link exists in any closed three manifold. This theorem, in a sense, very deep, and the proof is long, and it's not so easy, but he showed this theorem. And let me give an example, just an example of stably generic link. Let K be a figure 8 knot like this. Then a Zipf surface of K is one punctured torus, and we have a monodromy of diffeomorphism of Zipf surface, and we take a mapping torus of this monodromy, and consider the suspended flow of this monodromy on the complement of this knot. Then Ueki is my student, shows that the set of all closed orbit of this dynamical system, union of this the core K is a stably generic link. So this is one of the standard example of stably generic link. Okay. Then let me state the class field theory in topological class field theory. First, local class field theory. Let K be a component of stably generic link L, and the delta Vk is a boundary torus, the tube neighborhood of Vk, okay, and delta Vk is a maximal abelian cover of this torus, and this is a maximal abelian branched cover of solid torus ramified over knots. Then we have a class field theory for boundary torus knot. There is a canonical isomorphism, which is actually the Fulvix isomorphism, from homology group of boundary torus, the Gara group of the maximal abelian Gara cover of this boundary torus, such that we have the following exact sequences. Okay, so H1, so for homology of boundary torus plays a multiplicative group of the periodic fields. So, and this is VK is like a variation map of a periodic field. We have this commutative diagram. Okay. So now it's global class field theory. So let L be a stable generic link in an oriented connected closed C manifold. We define the ideal group of this the pair of C manifold and the stable generic link by the restricted product of H1 of the boundary class where K is running over the all component of stable generic link. And the variation of AK is 0. Variation means this map. Okay. The ideal class group is just co-kernel of the boundary map of the delta of H2. This is relative homology of H2M or L to the this ideal group. This delta is defined as a composite of this map in the relative homology and excision. Okay. This is very natural map in topology. Then we have map. The product of the reciprocity map of the local class field theory induces isomorphism, ideal class group, to the maximal, this is a project limit, maximal abelian cover of complement of L in M, where L is this L is a finite subring of stably generic link. Okay, okay, this is an ideal class field theory. Okay, finally, I give one problem for thesis. I give a Riemannian structure on the dynamical system, structure or dynamical system. For example, Benninger's Fourier dynamical system is suitable setting, gives a suitable setting for this. Then for finite abelian cover of the three manifold M, equipped with stably generic link, can we define the Archian function for a Galois representation, Galois character, and the Heckel function for a Heckel character of our ideal class group, so that we give an analytic formulation of global class field theory by Archie and Heckel. Okay. We don't know yet this kind of relation. Okay, so now I think we go to the part 2. I'm sorry, part 2 of my talk on the which is about arithmetic TQFT. But I'm sorry, I don't have time. So I don't have time yet enough. So I just give a brief talk of this subject. So based on arithmetic topology, we aim to bridge a number theory, three-dimensional topological quantum field theory, which have been developed separately after Gauss. And this leads to the arithmetic TQFT. And this was initiated to be studied by Myung-Hyun Kim and his collaborator, and then Hirano and myself. So maybe topological quantum field theory, maybe you know. So I just briefly reviewed. Sorry, I spent a lot of time to make topology. So according to Attier, and 2 + 1 dimensional TQFT is just a functor from the cobordism category of 2 manifolds to the category of C vector spaces. So we associate to the oriented closed surface sigma to quantum Hilbert space, oriented to compact 3 manifold M to the partition function of the quantum Hilbert space of the boundary of M, which satisfies these properties: multiplicativity, involutority, and gluing properties. Here is a picture. So if sigma 1, surface sigma 1, sigma 2 is cobordant by the 3 manifold M, then the partition function gives a homomorphism of the quantum Hilbert space of H sigma 1 to quantum Hilbert space of sigma 2 by the multiplicative and involutive property of quantum Hilbert spaces. Okay. In the physics context, this Zm is usually given by path integral, so it is not defined rigorously mathematically. John's polynomial in the Chern-Simons TQFT is such an example given by Witten. Okay, so here is a gluing property. Gluing the boundary is the same as a pairing, giving us pairing in algebraically, and closed three manifold obtained by gluing is gives some numbers, which is given by the pairing of Gm1 and the partition function Gm2. Okay, so now the Dirac-Witten theory is just 2 + 1 dimensional TQFT, which is defined by Chern-Simons action with finite gauge group. Okay, since this is a finite gauge group, the partition function is given by finite sum. This is fine, so it is defined rigorously. So, Dirac-Witten theory is an example of 2 + 1 dimensional TQFT, which is defined the rigorous way. Okay. So next we review the construction of Dirac-Witten theory. Okay. Dirac-Witten theory start with a finite group G and 3 cocycle of G with coefficient of R mod Z. And here is a notation. Okay, this is a notation for a compact manifold X with a fixed triangulation. We have the space of gauge field and the gauge group. And gauge group, modulo the gauge group, is the same as the space of representation of fundamental group D, modulo G. Okay. The key ingredient to construct Dirac-Witten theory is transgression homomorphism. This construction is due to Kiyonori-Gomi. And here is a transgression map. This is maybe too technical matter. So anyhow, we have the Chern-Simons 1 cocycle, Chern-Simons action as an image of this given three cocycle under this transgression homomorphism. We can define the Chern-Simons 1 cocycle, Chern-Simons action, and classical theory of TQFT is constructed by the following. The oriented surface, we have a Chern-Simons cocycle. The oriented compact 3 manifold, we have the Chern-Simons action. These are related to by this relation, differential of the group cohomology. Differential of the group cohomology of Chern-Simons action is a restriction of the Chern-Simons cocycles. And from Chern-Simons cocycle, we can construct a pre-quantization bundles on the moduli space of gauge fields. Okay. The quantum theory is we can construct a quantum, it's called geometric quantization. Quantum Hilbert space is just a space of the sections of quantization line bundle, and which is given by the function of the gauge fields, which satisfy this transformation law. Okay, this is a kind of non-abelian theta functions. It's classically, this was first introduced by André Weil in his paper of generalization of abelian functions. And the Dirac-Witten invariant is given by this type of sum of e to the 2 pi I of the Chern-Simons action here. Okay, this is a finite sum. So non-abelian, this Dirac-Witten invariants are kind of non-abelian Gaussian sum, non-abelian finite theta function. This is kind of theta function. Okay. So this is an example of Dirac-Witten invariant. Okay. If M is closed, C is trivial, it is just counting the number of representation fundamental group M to G. And if M is a double cover of S3 and the link is like this, under these and there is a linking diagram L in S3. Then the diagram Witten invariant can be computed concretely by this using the graph linking diagram of L. I omitted this. This is my result of my students. Okay, so now as I move to final section, let me give just 2 or 3 minutes. And based on the arithmetic topology diagram bit invariant, Min-Hyun Kim initiated to study the arithmetic analog of Chern-Simons gauge theory. It's called the arithmetic Chern-Simons theory. Okay, so here is a notation, maybe K is number fields, OK is a ring of integer, Kp is a periodic field, Op is a periodic integers before, as before. Xk is a compactifies the ring of integers, and Xa is a complement of the finite set of S. The pi p is the absolute Galois group of local field. Pi s is the étale fundamental group of complement of Xk. Is the maximal Galois group of K unlinefied outside S. Yes, and the given data is the same as a topological case. N is a fixed integer, G is finite group, C is 3 cocycles. We assume K contains the primitive S root of unity. And we take the representation of the local Galois group or global Galois group as a gauge field, Fs and XF, Fxs. Okay, the space of Galois representation plays a role of the gauge fields in arithmetic side. And we take a gauge group just by G itself, this G itself. Then Min-Hyun Kim constructed the arithmetic analog of Chern-Simons functional and the prequantization bundles. And in fact, Kim and his collaborator treated the case of G as a periodic Lie group. So Min-Hyun Kim and his collaborators are basically concerned with the classical part of TQFT. Okay. The construction of arithmetic Chern-Simons function as a prequantization bundle for more and more things are involved. So I don't have time. I have limited time. I cannot explain the details of this construction. And our results is that actually we constructed TQFT structures, arithmetic diagram Witten theory, for XF. This XF is correspond to, in topology, correspond to the case that the 3 manifold M is a ring complement. So this is a special case, but we can construct the TQFT structure. So namely, classical part and the quantum part. We can define the arithmetic quantum space, arithmetic diagram Witten invariants. Okay. So it's similar to the topological case. And our quantum Hilbert space, quantum space has multiplicative properties and involutive properties, and also the gluing properties. So here is a picture. This is now it's prime is like a knot. So XS is a complement of finite set of prime, and the VS is just a periodic. The union of periodic integers. Pair is in S, and then we glue this. Then arithmetic diagram Witten invariant is given by the pairing of these arithmetic partition functions like this. Okay, so I'm sorry, and also the same results of the diagram, arithmetic diagram Witten invariant similar to the topological cases. Okay. Okay. Yes, and finally, I maybe mention that our recent work, very recent work, this is in progress with my student Hirano, arithmetic conformal field theory, where we are now trying to pursues arithmetic analog, the so-called Segal bit and reciprocity law for loop groups, and it must be related to the Kubota Kazan-Patterson theory of metaplex theory of things. Is our recent my work in progress. Okay. Maybe this seminar is 1 hour, right?
Yes, yeah.
Sorry, yes, I spoke here.
Well, you can go on for a few more minutes if you want.
Yes, thank you for kindness, but it's okay. Maybe you can ask questions if you look at this file or later. Well,
thank you very much, by the way.
Thank you.
So, any questions or comments? So maybe I would like to ask one small question. So before your seminar talk, of course, we looked at your works on arithmetic topology, and you developed nilpotent class field theory for in the topological setting. So yeah. My question is the following: and especially in the local setting, you use the work of Koh, Labut, and Kuku, right? Yeah. So I mean, my question is the following: Koh later on developed meta-abelian local class field theory with Dechalit. So it is like local class field theory for solvable extensions of local fields of solvability degree 2. So it is two-step abelian extensions. It may be possible to develop a topological version of that theory, maybe. Have you ever thought about in that direction?
I think in topological cases, situation is much easier because torus, only we deal with the torus here. Only we deal with torus, so there is no fundamental group is abelian of this case.
Right.
So I don't know, maybe not. In topology case, it's much easier. So there is no abelian covering of a torus. So.
Oh, I see. But the nilpotent case is non-abelian also, no?
Yes, non-abelian, but globally it appears. Globally it appears non-abelian. Like this, global case it appears.
Right.
But
well, anyway, this is a question just for curiosity. I mean, we can maybe later on exchange emails in that direction.
Yes.
Yeah. So, Mehmet Akif, yeah. Please.
Yeah. I want to ask about in the beginning, there was a dictionary between topology and algebraic objects. Does it follow, I mean, the correspondence, is it functorial, or does it follow from something like Isbell duality?
like the usual case, or?
Excuse me, where the?
I mean, yeah, this dictionary here, is it functorial? I mean, or is it some form of Isbell duality?
Functorial in which sense?
I mean, for example, I mean, does it send the maps here in that sense?
Functorial in which sense?
I mean,
if we were to create, say, maybe I'm going to try to interpret Mehmet question, functorial in the sense that if for all the objects in the first column, we were to create a n tuple consisting of a selection of those objects with proper embeddings, and the same on the number theory side, would there actually be a functor
between rings?
specified?
I see. You mean that is there a functor from topology side or number theory side, or you mean that side?
Yes.
I see. I don't know.
Okay.
It's fantastic if we can get such a, but this is just analogy.
Something like this.
Conceptual analogies, like analogy of function fields, number fields, is just same as conceptual analogies.
Oh, okay.
But maybe I should add or ask the following question. So in the class field theory you developed, for example, in the classical version of class field theory in number theory, reciprocity law satisfies certain basic functorial properties like transfer functoriality and so on and so forth. So in the topological setting, there should be analogs of these functorial properties, right?
Right. Yes. In the topology case, it's also that such a functorial property is satisfied. Yes.
That's great. Yeah.
Thanks.
So any more questions or comments?
Yeah, I have one. I mean, I probably have more than one, but I just want to point out one in particular. When so I mean, there are these diagrams with primes and linking numbers among primes, or seeing a prime as a link. So in those diagrams, to what arithmetic property among the primes or prime relationships would those things correspond to? Is it like specifically like down to earth classical number theory sense of either ramification or solvability of specific equations, or how the number of solutions of an equation in different number fields would relate to each other? Is it something like that? Or to do with the, when you say monodromy, to do with some automorphism?
Yes.
Yeah, there's that.
I'm sorry, I don't see that. What maybe I just can't hear well what you said.
This is in later slides. I mean, this is maybe the first appearance of it, but there was another one where you drew from the work with some of your students.
Yeah, some of my students. You mean these things?
Yes. That, for example, that one.
Yeah.
So, I mean, does this diagram encode some piece of information about arithmetically or not on number theory side? What does this diagram encode or tell?
I see. Yes, then I can I can tell you that. Yes, this diagram encodes that. Okay, this R4, this extension, determined by 5, 101 and 8081 by these 3 prime numbers. This R4 is constructed. Okay, and then this 449 is completely decomposed in this extension if and only if the Milner this is 0. And actually, yes, I'm sorry. This is not in this case. In this diagram encodes that 449 doesn't completely decompose in this extension.
So it's kind of like the tower of field extensions, except with the property of how the degrees collapse or multiplicativity of the degrees.
Yes. If you write down everything and then the completely decomposition, such a business is finally it's given by some equation. It's modulo some prime or something. In elementary terms.
Okay, so then back to maybe Professor Iketa's question, I mean, in tower of extensions, solvability or abelianness of extensions or non-abelianness of extensions also sort of come up. So then, would it be possible to translate that question to something specifically in terms of these diagrams?
Yeah.
Can we see properties of solvability or abelianness of extensions in these? Read it from the diagrams, so to speak.
I think that your question maybe, is this related to the third question?
Yeah.
But we don't have answer to this.
Okay. So so that's a good place.
Only Gauss's reciprocity law and the symmetry of red-eye symbol was also verified before, but for n is bigger than equal to 3 as 4, I think nothing is proved for this. Nothing is known about this.
Okay. Actually, Professor Morishita, problem number 3 is also related to the last thesis problem that you posed also about Hecke L function and Artin L function in degree 1 situation. The higher degree version should yield the topological version of Langland's reciprocity, right? And it should correspond to relate to number 3 probably, because right, I mean Langland's reciprocity states that Artin L function. So there should be a correspondence between Galois representations and representations of certain algebraic groups of say of GL n of F, say if it's n-dimensional, in such a way that the respective L functions should match. So the question thesis problem that you posed in the very last page.
I see. But I'm sorry.
Is the abelian version.
But I don't know how to define the Adele ring.
This is the basic problem actually. That was we were discussing yesterday with Semih, I mean, and that was I was going to ask you. So Adele is very fundamental, but how to define Adele of or how to define a ring whose multiplicative group is your Adele group and which encodes certain arithmetic information. some group algebra
Yeah,
kind of thing one
yes.
has to consider.
That's that's fantastic, but I don't know. I don't know how to define that such notion.
Yeah.
There is, but in three-dimensional topology,
Yes.
in some sense, it's some similar. There is known some theory which is similar to the Lagrange correspondence. It's called S duality in TQFT.
Well, I guess Kapranov is kind of S duality in TQFT. Let me take a note. Yeah. Yeah, there is this famous article of Kapranov on analogies between TQFT and Lagrange's program. His aim is
I forgot he defined the Adels in topology side, or I forgot. In TQFT, yes, maybe we should compare. If you want to go to the Lagrange direction, maybe this is our theory is more elementary, very elementary theory. But if you want to go to the Lagrange direction, maybe you may compare the number theory and quantum field theory. It's not this case. Our theory is very elementary topology. So maybe quantum field theory maybe contains some feature similar to Lagrange correspondence.
But your theory should be the one-dimensional case of the topological version of Lagrange. I mean, right? I mean, in the
yes,
arithmetical setting. Yeah. Well, thank you very much. Excellent talk. Wonderful talk. Any more questions or comments? So let's thank once more.
Well, thank you. Well, I'm happy to meeting everyone in this room.
Well, we are very happy to meet you and listen from first hand on arithmetic topology. Thank you very much.